Hello and welcome back. Today we will continue to look at problems involving water and steam so that we know that we have understood this concept properly. As with all other problems, I would suggest that you pause and try to solve it on your own before you look at the solution here. So, this problem says that 1 kg of water at 0.2 megapascal is initially enclosed within a volume of 0.1 meter cube in a vertical piston cylinder arrangement. So, I am going to draw that. So, we have a vertical piston cylinder arrangement. So, that is 1 kg of water. The initial pressure is 0.2 megapascal and the initial volume is given as 0.1 meter cube. It says the piston initially rests on stops. So, we have stops here. Of course, you understand this, there is actually no gap. This piston is frictionless, it will be just touching the inside surface, but this is only a schematic and not necessarily very accurately drawn. And this piston will move when the pressure is 1 megapascal. So, we have the weight of the piston plus the atmospheric pressure outside being equal to 1 megapascal. So, pressure due to piston plus atmosphere is 1 megapascal. So, what we are given is during a certain process an amount of heat equal to 2500 kilojoules is transferred to the water. So, we have a process in which 2500 kilojoules of heat is transferred and we are asked to find out the work done and the final state of the water. Okay. So, what we know is that this has initially water at 0.2 megapascals. This piston can only move if the pressure is 1 megapascal. So, if you now heat this with this 2500 kilojoules of heat. So, there are a couple of things which can happen. First is that until the pressure here becomes 1 megapascal, this heats this water and whatever is there, water in either liquid or vapor state or a mixture of both at constant volume until the pressure becomes 1 megapascal. So, if with this amount of heat, if the pressure does not cross 1 megapascal, then this is a constant volume process. If with this heating the pressure becomes 1 megapascal, then it is going to be a constant pressure process until a certain point of time, until whatever heat is given is sufficient to be to move this piston, whatever distance it can move. So, let us first find out what is the initial state. We know that the mass is 1 kg, the pressure is 0.2 megapascals and the volume is 0.1 meter cube. So, I am going to try to see what is the saturation condition for this pressure. So, I am going to see at 0.2 megapascal. So, what I need now is the steam tables. So, I have the pressure as 0.2 megapascals, so which is here. So, at this condition the temperature is 120.2 degrees centigrade if it was saturated. If it was saturated, the volume of 1 kg, if it was completely water, the volume would be 0.001 meter cube. If it was completely vapor, the volume would be 0.885 meter cube. So, what we have here is that the volume is 0.1 meter cube. So, 0.1 lies in the range between 0.001 and 0.8857. So, that means we must be having a mixture of water, liquid water and steam at this condition. If for example, the volume of 1 kg was greater than this 0.8857, then we would conclude that it was in the superheated state. If it was smaller than this, we would conclude that it is in the liquid state. So, that is something which we can find out. So, now I am going to write down these values. So, I have 0.001061 and 0.8857. So, at saturation, at the temperature of, I think that was 120.1 degrees centigrade, we will confirm that 120.2 degrees centigrade. This would be the volume, specific volume of water liquid, and this would be the specific volume of water vapor. The specific volume we have here, V1, is essentially this, which is 0.1 divided by 1 kg. So, then since this value lies between Vf and Vg, therefore, at condition 1 we must be having a saturated mixture. So, as I said earlier, if our V1 was greater than Vg, it would mean that it was superheated, because then the volume is higher, and if V1 was less than Vf, then it would mean that it is either compressed liquid or it could be, for example, solid, depending on what the value was. So, in this case we have it a saturated mixture. So, since it is a saturated mixture, we should be able to find out the quality. So, we said that we can generally write V as either 1 minus x into Vf plus x into Vg, or Vf plus x into Vg minus Vf, or Vfg is what we are calling this. So, I have here, this is 0.1, and what I am looking for is x. So, I have this as 0.1 minus I'm going to find out this value. And this turns out to be 0.11, 0.112. So, this turns out to be the quality at state 1. So, initially the process is a constant volume process. So, what I can try to see is, if I add this amount of heat, what will be the final state I get to, or if I can also try to see that if I want to reach a pressure of 1 megapascal, how much heat do I have to add from this initial point. So, that is what I am interested in finding out. So, for the constant volume process, so I have V1 equal to V2 and V small 1 is also equal to V2. So, from the first law for this process, I have du, I am ignoring potential and kinetic energy and so on. I have this is a constant volume process initially, this is 0. So, del q should be equal to du, or q during the constant volume part of the process is going to be equal to delta u. So, I can find out what will be the change in energy. So, I need to find out the initial energy of this u1. So, u1 would be given as uf plus x into ug minus uf So, I need to find out UF and UG. These are the same condition of 0.2 megapascal pressure and saturation. So, let us look at what is UG and UF. So, UF is 504.5 and UG is 2529.1. So, I have 2529.1 and 504.5. So, let me find out what this is. So, I get a value of 731.25 kilojoules per kg. So, my U2 over here is the point where the pressure here is 1 megapascal. So, and the volume is still the same. So, the final volume is 0.2 meter cube at V2, specific volume is 0.1 meter cube per kg. So, let me see what would be that state. So, I am going to look at 1 megapascal with a specific volume of 0.1 meter cube per kg and find out what state that is, what phase that is. So, if I go to this table here at 1 megapascal, I am still looking at saturated table. At 1 megapascal, the liquid volume is 0.001127 and the vapor volume is 0.1944. So, what I see is at 1 megapascal, whatever is the specific volume I have lies between these two values. The value I have is 0.1, which is greater than this and it is less than this. Therefore, even at 1 megapascal, my condition is at saturated condition. It lies between these two, so it must be saturated. So, at 1 megapascal, the saturation temperature is 179, which is okay. I do not need that immediately, but what I need are these values 0.001127 and 0.1944. Confirm that I have the values correctly. Yes, I have 1127 and 1944. So, V2 is greater than Vf and our V2 was 0.1 meter cube per kg. These are also in meter cube per kg. And V2 is less than Vg. Therefore, 2 must be in the liquid vapor dome. It must also be in the saturated condition. So, I can find out x2 the same way in which I found out x1. So, I have V2 is Vf at this condition plus x into Vg minus Vf. So, x is all of these at 1 megapascal. I have V2 is 0.1 minus Vf is let us find out this. So, this comes out to be 0.511, actually 0.512 rounded off. So, we see that the quality has increased in this process. We have added heat to it. So, in the process some of the liquid has become vapor, the pressure has gone up, and so we have a higher quality here. So, let us find out U2. U2 is essentially UF2 plus X2 into this. So, again we need the values of UF2 and UG2. So, we can find this from the tables. UF2 is at 1 megapascal. So, the value is 761.4 and 2582.7. So, it gives us a value of 1693.9 kilojoule per kg. So, we can find out capital U2 minus capital U1, that is M into U2 minus U1. M is 1 kg, this is U2, and we had just found out U1, which is 731.25. So, which is 962.65. So, what we see is we are giving heat to this process. The amount of heat we need to reach this point is less than whatever we are giving. So, we are giving 2500 kilojoules of heat, if out of which by the time we have given 962 we reach this state. Supposing this was smaller than this, it means we would not have reached this state and we would have had to find out where we were earlier, but we have now already reached the state. So, whatever is remaining will now be used up in a constant pressure process after that. So, what we can see is out of this 2500, 962 is used up for this, and we have 1537.3 kilojoule, 0.35 kilojoule left for the constant pressure process. So, we can now see what happens in the constant pressure process. So, if you were to look at a PV diagram where we can see the work done. So, initially we are in the dome region. So, initially we were at a pressure of, I think we were at 0.2 megapascal. So, we reached, by heating this, we reached a state where we are now at 1 megapascal. We went in a constant volume and constant specific volume process to 1 megapascal. And after this we are still not at saturation, we have some dryness fraction. So, let me draw that. So, we were initially at a dryness fraction of about 0.1, and we have, so clearly my shape of this dome is not very correct, but we were initially at a dryness fraction of about 0.1, and after heating we went to a dryness fraction of about 0.5. So, I am not able to draw the dome very correctly yet to reflect these two values, but what we see is that over here, so this must be something like this. So, over here the dryness fraction was smaller, over here the dryness fraction is larger. So, we went from some point 1 to some point 2 here. After this, we are going to have a constant pressure process till we reach some point 3 over here. That is essentially the process on a PV diagram. So, we need to now find out this point 3. So, we can see what we have here. So, after we have reached this point 2, the process is essentially P equal to constant, because it is now lifting the piston against a constant weight and constant atmospheric pressure. So, from the first law, we see again we have this, but this is a constant pressure process. So, for a constant pressure process, we know that this is essentially P dV, and we have done this earlier. We can club this du and P dV. So, we have du plus P dV is del q. This is P dV, you can add V dP to it, because dP is 0, it is a constant pressure process, and this essentially becomes dH is essentially del q. So, we know how much of heat is given here. So, it is 1537.35, or I can write so what we have is this, the mass is 1 kg. So, I will take out the mass already. So, I have this. So, what I know is that this 2q3 is 1537.35 joule. I can also divide by m. So, this is joule per kg is equal to H3 minus H2. So, from the tables I can find out the value of H2, which is at 1 megapascal with the appropriate quality, and then I can find out H3. So, that is what I am going to do. So, I want H3, which is 1537.35 plus H2. So, this is what I need to find out. In order to find out this, I first need to find out H2. So, H2 is essentially HF plus X into HFG at 1 megapascal. So, let us find out these values. So, at 1 megapascal, HF is 762.5, HFG is 2014.6. So, I have 762.5 and I have into X, which we found here as 51.512. So, this gives me a value of so, now I can find out Hc, which is this plus this. So, this is my final enthalpy. For this final state 3, what I know is that the pressure is still this 1 megapascal and the enthalpy is this value. So, I now need to find out something about that state. So, let us see what else we are asked to find out the final state. So, let us find out the work done. The work done is essentially this PdV, that is the work done. So, I can find out that. Let me also find out the final state first, which is possibly easier to do. So, I am looking for a condition which is at 1 megapascal with an enthalpy of 3331.32 kilojoule per kg. So, if I go back to this steam tables, at 1 megapascal, if it was saturated vapor, it would have value of enthalpy of 2777 kilojoule per kg. The value which I have, which is 3331, is greater than this. So, therefore, it must be superheated vapor. So, I now need to go to the superheated tables. So, I have here the superheated tables. I am going to look at the table which is at 1 megapascal of pressure. So, which is this table. I need an enthalpy of 3331. What I see is that the enthalpy here is 3264 and here is 3371. So, this is at 350 degrees. I am looking here in this row corresponding to 1 megapascal. So, in this row I have the value of 3158, which is not useful to me. I need 3331 lies between these two. So, what I am interested in is the values at 400 and 450. So, I can actually interpolate and find out what would be the temperature, because I have 3331 which I want, I have 3264 and I have 3371. So, I can find out where it lies between these and correspondingly interpolate the temperature for a more accurate value. So, I could do that or I can just leave it as an exercise for you to do. And what I am also interested in is to find out what is the work done. Or maybe I will do this anyway. So, I have 3264.5 and 3371.3, 3264 and 3371. This is, I think, at 400 degrees Celsius and the other is at 450 degrees Celsius. So, my value is essentially what we had here, 3331.32. So, I can do something like, I am just going to interpolate. So, I am going to do, like, for example, T minus 400 by 450 minus 400 should be the corresponding enthalpy minus the enthalpy at 400 by the enthalpy at 350 minus the enthalpy at 400, linear interpolation, which gives me which tells me that T is about 431.3 degrees Celsius corresponding to this value. So, I have the value of T also. So, my final state is fixed. So, my final state is 431.3 degrees and 1 megapascal. So, I can indicate that here. So, I have on a PV diagram I have isotherms which go like this. So, I am now looking for an isotherm which has which cuts somewhere here. I am looking for a 430 degree isotherm which I know will cut somewhere here, and that is my point 3. We are also asked to find out the work. It is a constant pressure process. I can find it as PdV, or I can also find it as del Q minus du. Either of these is fine. So, I need so for the work from 2 to 3, from process 1 to 2 there is no work done because it is a constant volume process. This is either P dV, pressure is known, I need to find out volumes, or I can also find this as del u. This m in both these cases, and m is only 1 for this problem. So, I can find out either of these. So, let me see what I already have at state 2. At state 2, I knew the specific volume. So, I will possibly use this formula because I do not think I know the, I can find out u2, okay, I have u2 also. So, any of them is okay. So, it is the same number of steps for me. So, let me use u because I have u2. u2 is 1693.9. I need to find u3 in the similar fashion. So, u3 I can interpolate. I know that at this temperature I need to find u3. So, what I can do is I can do I know the temperature now. What I am looking for is u. I can interpolate like this, or I can interpolate using enthalpies. So, this will also be equal to, for example, u3 minus u at 400. So, I know I need to get these tables again. I am looking at the 1 megapascal table, and I am over here. So, this is 2957.9 and 3040.9. So, since I have these values written here and I am a little lazy to recalculate, I am going to use this, or I can use this here. I know T3 also, so I can use that there. So, let me do that. So, this comes out to be 3009.85 from here, using any of either this and this or this and this. T3 is now known, and the work interaction is mass into u3 minus u2. u3 is this, u2 is this, which gives me a value of 1315.9 kilojoules. So, in this way I have both the work done in this process as well as the final state. So, final state is pressure of 1 megapascal, temperature of this, and it is superheated steam. That is essentially what I see.